Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about soldering irons or about this puppy. Let's dive deep into it. So what exactly is our need? What do we need in the first place? Well, we need a way to cause control melting of solder. Basically, we do not want everything to melt precisely exactly what we want to melt. Nothing more, nothing less. So we want something that has good temperature control and dexterity. This is also another critical aspect. You can't use water heater a heating element to do this, because again, it would be much user. It won't have the dexterity needed. So size also plays a role, and depending on your component size, it also plays a very critical role. If you are dealing with something like, let's say, SMD, surface mounted devices components, those puppies are tiny. You cannot use a big ass heating elements for that. So you have to use very small soldering irons. Otherwise, you will literally touch other elements on the same motherboard. So what sort of temperature we are looking at? So we are looking at, if you are dealing with lead free, which nowadays should be used, that is 217 degrees Celsius. In Fahrenheit, that is 422 degree Fahrenheit. Lead based system would only require 183 degrees Celsius, around 361 degree Fahrenheit. Now be mindful, if you ever looked at any temperature control system of a soldering iron, you must have noticed they do not have this temperature. They have much higher temperature. For example, even a cheapo like this has a temperature starting from 200 degrees Celsius and it goes to 480 degrees Celsius. 480, right? 450 degrees Celsius. Now question is why? Well, you have to understand, you are talking about thermal flow, meaning heat has to flow from here to there, and that flow cannot happen if there is no delta. So at the beginning there is a lot of delta. This is an ambient temperature, let's say 30 degrees Celsius, and your iron is at, let's say, 217 degrees Celsius. Lot of energy will start to flow, but it will soon equilibrate, and it will not equilibrate at this temperature. It will equilibrate much lower than that. So maybe you are only getting 200 and not even 200, you may only get 150 degrees Celsius. So that is why, to make sure that heat flows efficiently, we have to create an increased delta. Either you improve the contact, which is very hard to do unless you are using laser soldering, but if you do not have that, the next best option is increase the temperature. That's why all soldering irons generally have bonkersly high temperature. So 270 degrees Celsius, 283 degrees Celsius. Now you may like, what if I want to do low temperature? You have to have large thermal mass. Basically, if you are dealing with something big, you will see people using solder gun which have much more thermal oomph. So it can just flood. Basically, it does not have the temperature to force energy through. It has just enough energy to just force through. So you have to do that. So these are the two options that we have. Then one of the critical aspect, it should be safe to handle. We can easily make a glowing rod that is super hot, like you can easily do that, but it has to be holdable, right? If you cannot hold it, what's the point? And it has to be at safe temperature, and that's the biggest difference between a cheapo one and expensive one. You will notice it. In cheapo one, first 15-20 minutes nobody cares. 1 hour, 2 hour, then you will notice that these puppies will get hot, uncomfortable, to almost causing minor skin burns. And yes, they do, especially if you use them for 1 hour or 2 hours. Most of them won't last that long, but you will notice it. You will notice it. So that's our requirement. So what is the logic behind it? Well, logic wise, we need a heat source. Obviously, we need to melt something, we need heat source. So generally only 4 primary options would be available. One, you have gas. It's no longer in vogue right now, but it still has some advantage, especially if you want to have a soldering kit placed somewhere. If you're like, hey, I want to put this kit here and forget about it, and it still has to work without a grid. So people actually still use this. Like you can find a remote cabin where, let's say, they are doing ham radio operations. If they are like, hey dude, we need to put something here that will be working long after, like, long being neglected, this works. And be mindful, even though it uses fuel, it does not use open flame. You just ignite it with open flame. They have a catalyst. Catalyst is the main reaction. And in terms of heat, you do not have to worry about it. It's like, bro, I got this. This is that sort of oomph, the thermal inertia these puppies have. You do not have to worry about it. But generally, they are not preferred for minute works. They are basically a very specialty tool. Back in the days, was very desirable, but nowadays not so much. Then you have battery powered, because of the development of USB-C power delivery, the fact that you can have a lot of amps, lot of voltage available in just USB-C. This sort of iron started to become a very mainstay, and because of the cartridge style heater, I'll talk more about that. They can actually do some serious work. Like, unless you are dealing with some gigantic ground planes, these puppies are like more than enough. Like for more than enough people, this is like, buy this and forget about everything else. They do come expensive, and they do require you to have a good power bank and make sure you keep power bank charged. That's why I said, like, it's still this still has that put it and forget it benefit. So you have gas, you have battery, then you have DC power supplies. DC power supplies are generally, anytime you see a power station, not all of them, let that be very clear, but many of them, it does not make that much of a difference if it's DC or AC, but many times you will find something that is DC, many times you will find something that is AC. So you will have AC mains line coming into your converters station will do the step down, then it will make it into DC and then send it there. Sometimes it just might send the AC itself, because again, heating element is one of those things that does not care too much about AC or DC. DC will, if it's a good DC, it will just give you rapid response, because again, it does not have to wait for that system. So DC is like is there. And then you have AC mains, something like this super cheap puppy. I have no idea why the heck it has ground probe. It's not grounded. It's not ESD safe, so it doesn't, for some reason it has it, which is ironic, because it does have this one has a method of properly grounding it, but it has only 2 prong logic, Chinese logic. So that's there. So what about the power rating? Now this depends on your work, what you're doing. Meaning, if you're doing light duty works and all, something very brutal, this will be more than good enough. But let's say you are working with drones, and those puppies require like thick wire with a lot of ground plane and a lot of soldering. Yeah, they will reach a point where it's like, bro, me good, but not that good. So at that point, you will be like looking for something like this or something like this, where it has more oomph. That depends on your working parameters. What are you working on? Like if you're working on mobile phone, this is more than precise enough, more than powerful enough. So, and it generally we prefer something that has a feedback loop, so you can control it. Now you can have a blind feedback loop where it's just monitoring the current that is being consumed by the device, and it's like, hey, it's not consuming too much current, let's tone down the power. It started to consume it, okay, let's dump the power. Like, why would you want to do that? Well, here's the deal. If iron kept, like you just put it there and you kept the iron at maximum temperature, it will overheat. You do not want that. You want to be like, hey, if it's actually dumping the energy into a solder ball or ground plane, the temperature will come down. You want a lot of energy going there at that point. But if it's just standing, like, idling, which most of the time it will be, yeah, at that point you are just overheating it for no reason. So at that point you want your energy to, so that's a dumb feedback loop. In very old days, analog systems had that. But nowadays we do want temperature feedback. That's better than nothing, but you still do want temperature feedback and power regulation, how the heck power is, especially with ESD safe equipments. So you really do not want to be the person who fried a very expensive motherboards because your basically soldering error was not grounded properly. And yes, people have lost equipments. That's why we learned that you need to have that. And again, if you're buying anything made by any professional company, even competently professional people, you do not have to worry about it. But if you're buying a cheapo, be mindful of it. So these are the logic behind it. So let's understand the control part of it. Control part is basically when you are dealing with professional, meaning this is a tool that you use as a breadwinner, so to say. In those scenarios, you need proper level control. And if you don't, you do not have the ability to do your job properly. So if you have too much energy, this is the most common mistake everybody does when they just get started. It's like, buy the biggest, most badass, powerful heater you do and just go YOLO on it. And yeah, it does work, but soon you'll realize this board is not made out of magic. It's fiber boards. It's like, fiber FR4 board. So it's not indestructible. You can overheat it. And again, this do get heat up to 400 degrees Celsius, meaning if you kept it at one point for too long, you would eventually reach a point where these things itself will start to heat to 300 or maybe even more than that. So you will literally fry off things. And yes, I was stupid enough to actually, when I was trying to desolder something, I did not know how to do it properly. I literally melted the lead off of a transistor. So you can fry things. So going for bigger is better. It's not always advisable. And then you have other side also. You may be like, hey, what if I cool down the temperature? Again, because be mindful, even though your tip could say, hey, I'm at 300 degrees Celsius, and it could actually be 300 degrees Celsius, it may not have enough delta to dump enough here to do proper welding. So even though you have a hot rod, you're touching a hot rod to a cold point, the cold point may only come up to, let's say, 200 degrees Celsius. If it's a lead free, it will look okay, but it would be a cold joint, a cracked joint. So you do understand, right? It has to be precise. That's the control that we seek for. That's why you have so much electronics in the control station. That's all there is to it. It's like, we want exactly the right amount of heat. We do not want too much or too little. So we need to be just right. If you do not have just right, yeah, it's going to be hard to do your job. That's one of the, and closed loop temperature control is desirable, and it also allows you to increase tip life, because some of the smart controllers nowadays, they have the wisdom to be like, hey, the tip is in the holder. Again, they have a feedback loop from the holder also. So it's like, hey, what if I tone down the temperature to 150 degrees Celsius, not off? Why don't you want to turn it off? Because you will be going from, let's say, 350 degrees Celsius to 0 degrees Celsius or ambient. So that's a big shock. And again, when you pull it out, it start to heat it up again. Again, the shock is bigger. So you do not want huge shocks to your element. You may be like, hey, let's go from 350 to 150 degrees Celsius. And of course, it will have a cutoff where it's like, hey, it's not been moved for like 5 minutes. It will be like, okay, let's cut it off now. Again, gentle slope down. It's much easier on the ceramic, much easier on the heating elements, much easier on the stuff in the chain. And again, if it's like you are putting it down, doing things, okay, now you're pulling it out. Again, it's much easier to go from 150 to 350 rather than going from 30 degrees Celsius to 350 degrees Celsius. So you do need closed loop control system. You do not want cold joint. You do not want to over fry your stuff. And that's why whenever you see people, YouTubers who are dealing with soldering station or professionals, they have this sort of thing. Why? Here's the deal. The temperature coming from the inside of the box, basically your temperature controller, it's inside the tip. You do not know what's happening at the tip. And that's why all professional systems have a way to calibrate it. You need this sort of meter if you want to calibrate it. Even if it's a very high-end one, again, high-end one will not drift very quickly, but you still do not know, you're still trusting it. So we generally have an external meter where you can test the tip temperature, precisely what's happening here. And benefit of that is now you can calibrate it. It's like, hey, I set it to 350. It does not mean that the tip could go to like 400 degrees Celsius. It does that. Many cheaper ones, they do that. They do overshoot the temperature. It feels like, oh, I set it to 350. It's heating up so quickly. And like, is there a penalty to that? Yeah, penalties. There are many modern silicon components that are thermally sensitive. You could cause hysteresis into them, meaning permanently damaging them or changing their behavior. You do not want to be that one. That's why people spend a little bit of money. These are not that expensive. You can buy them and just like calibrate it. And people generally recommend it to do it every 6 months. Because be mindful, tips change, tip oxidizes, you clean it, your flux goes through it. So things change. You do need a way to calibrate. That's the control logic behind it. That's why we have so much stuff. Many of them have like full-fledged microcontrollers, or like sometimes they have like full-fledged computer there just to manage soldering irons. So that's the control aspect of it. So now let's look into the two core developments that have happened. So because we did not have a proper naming convention, so the old one is just called old one, or let's call it, that's how we started. And then you have cartridge one. So how did we start? We started with the ecosystem of this puppy, basically. So, oops. Okay, so this one, what you have is a base body. The body itself has the heating element, meaning if I want to change the tip, I will open it up and replace the tip, and this is my heating element. The heating element, and if you bought an expensive variant of this, it will come with the temperature probes also. You will find 4 wires, 2 wire for the heating, 2 wire for the temperature readout. So that's how old days we used to get temperature control. It works, but problem is you can see that like there is a ceramic element. Now I put a tip on top of it. There is a gap, right? The tip is not precisely bonded to the heating element, and you were like, does that cause issue? Yes, that's why these things have to be 400 degrees Celsius. And that's why they have to be very high power also, 30 watts, 50 watts. Be mindful. If same amount of power, 60 watt of power, like 60 watt of this design versus 60 watt of cartridge, would be night and day difference, because energy is not going there. So this is how we used to handle it. Basically, handle used to have heater, and we just used to replace tips. Tips, you could buy something like this, tips. So tips you can replace, but be mindful, tip requires disassembly. So if you had to, many people just bought 2 or 3 irons. If they needed to switch between tips regularly, they're like, just buy 2, 3 irons. It's much cheaper, much more easier to do. So this is how the original way of doing things. So now we have upgraded to this design. This is cartridge based system. So cartridge based system is like, people figured it out. It's like no matter how you built your tip, it's not gonna last, but you are wasting a lot of energy. So if you have this design and you are forcing a very high temperature unnecessarily. So somebody came up with the idea, what if the tip itself had the heating element, meaning this element is bonded to the heating element. The temperature sensor is bonded to the heating element. Basically everything, the heater source, temperature reader and the tip, all 3 are in this area, very small area. So benefit is basically the efficiency of thermal electrical energy going here, heater heating up, temperature sensor reading the heat, controlling it wisely, and your solder melting, all of them is very efficient. That's why 60 watts of this design, 60 watts of this design would be night and day different, because this would be at your tip, it would be barely, let's say, 20 watts of heating power. Like, wait a minute, that's bad. Yeah, that's why the heat is going everywhere where rather than where you want it to go, because of the inefficiency. That's why every company is now moving into this, and that's why that USB-C power bank based system requires cartridge based. If it was using the ceramic heater, it will barely do anything. It has to be a cartridge, otherwise it will simply not work. It will waste most of the energy jumping the air gap that is there. So this is how we used to be. Now everybody's like, okay, this tips, and you will see generally 3 points. So 2 of them would be for heater wire, 1 of them would be for temperature sensor, and 1 would be shared. Not all of them have the same design, but generally this is the philosophy. So you temperature, basically the thermocouple and the heating element, all of them are in the cartridge itself. And cartridge is what we call tips, or sometimes called pen, and this is what you swap. So swapping, you can see, it's much easier. You can swap out tips much easily. And if you the station is the expensive component now. It's almost like ink tank. So the station is very expensive, but the tips are low cost comparatively speaking, and they do last longer compared to these designs. And again, they consume less power. So if you are talking about stations where people are actually doing it, you will have a little bit of savings in energy also. And these come in various sizes, shapes, design, whatever have you. So there's a far better heat flow characteristic. It's law of physics. It's like, if heat is created directly dumped into the material, the only unknown for me is like, how the heck they have the electrical insulator and thermal conductor that works at that temperature. Because again, these things do get hot. So you are looking at something that should be stable and safe at 500 degrees Celsius. I do not know which specific ceramics they are using. And most of the design, they will just show, oh, it's copper. It's like, dude, if you just have raw copper, it will cause a short circuit with the heating. So heating element does require some isolation, electrical isolation. How they are doing it, I do know some ceramics can handle it, but like, how would you do that? Some people have tried to do it in your home. They used plaster of Paris. It does work, but it's not 500 degrees Celsius level work. So if any of you know what exact insulation they use inside it, I would love to know. So again, it has to be a very good conductor, and it has to be a very bad electrical stopper. So it has to be great at electrical insulation and great at thermal conduction. Difficult things. Magnesium oxide maybe. So cartridge are much better design. It has much better heat flow characteristics and much longer lasting. And be mindful, sometimes people have this issue of like, is it copper or is it iron? So these tips, generally they are iron. Have a magnet, test it. And if you buy something different, like these come with copper, so magnet do not stuck with that. Now you're like, why? Well, copper, while it is a better conductor, and all these systems do come with copper, all these are copper based, but they generally have a very strong coating. Without coating, the flux that is used will eat away your component. Literally, it will literally etch away your tips. So for that reason, they do not last. They require a very strong coating. What coating? Most of the time it's nickel, and then let's say the tip could be nickel, and then this part would be chromium. Like, why would you want dual coating? Well, dual coating is needed. You don't want to solder to wick to these areas. No? You only want them to wicking that area. So generally 2 sides of coating is done, even in this designs. So one coating is in the tip where they want the solder to stick. Other coating is something that solder does not like to stick. Solder cannot wet to. So coating is a very big part of engineering of these puppies. So many times people will say, hey, you can have a soldering iron and replace the steel one with copper one, you'll get better output. Yes, absolutely you'll get it. You just won't get the lifespan unless you know how to do coating. And yes, some people have figured out. They just grind everything away with a file or a rotary tool, small rotary tool. You can grind everything away, and then you can just put it in an electroplating bath and just plate it with nickel. Now you have a proper pro grade copper conductor which will behave better. So if you have iron based system, coated one, the let's say performance is X. So you rebuild the same thing using, let's say, tip like this. You use the same thing, copper tip, and you go through all the process of tipping and all that. It will give you better performance. But again, you can buy it, flat out buy it, but it's expensive. So that's the characteristics of it. Cartridge, better, more expensive. This system does work, but not desirable. And be mindful, for mobile phones, is generally it's like just accept it. Just accept it. Mobile, because again, components are so small, you do not want something like 400 degrees Celsius there. And because the tightness of everything, the heat producer, the reader, and the tip that is acting, the closeness of this, the control is very tight. It's like these things can dump reliable heat at, let's say, as low as 280 degrees Celsius. They can be like, I got this. I can dump that much energy exactly where it needs to go. So flat out, old, this is literally going from 3G to 4G. It's like fundamentally better. Now let's come to the final part of it. It's an art form. Let that be very clear. Many times people do get a bit too involved into this, like this is how you do it, this is how you not do it. This is like, you do not have to worry about it, because fundamentally it's art form. Because is it a necessary skill for electronics? Absolutely. You must know, must be competent enough where you can do that. Heck, I can do it, so I'm reasonably sure all of you can do better than that. So that's easy. Now, where do we actually use it? Where do we like justify those sort of devices? Prototyping, low volume production run. Then you have core component, basically component level repairs. Basically, if you are an Apple repairman, you do not need a soldering iron. All you're gonna do, take this, open things, yeet the component, put a new component, and charge like arm and a leg and a kidney. But if you are Louis Grossman, you're actually going down. Okay, why the heck this MOSFET is not working? Why the heck this capacitor blown up? If you want to desolder them and put something, yeah, now you need a good soldering iron. If you do not have that, your job would be difficult to say the least. That's the whole point. And why I'm calling this more of an art form? Well, here's the production, like where you are producing millions of these things. Yeah, you do not use that. Nobody is using this, puppy. I would love to see this. This is 500 watt soldering iron. You have to know, for those sort of scenario where you are producing mass producing devices, we use reflow ovens. We have let go of the idea of soldering. We realize that it's not, basically imagine it this way. How can you be precise enough with a human hand where you're like, okay, put this here exactly for 5 minutes and then pull it off. Put it here for exactly 1 second, then pull it out. Yeah, it's not happening. So for that reason, we utilize reflow ovens. Sometimes they are heated air, sometimes they are infrared baked, sometimes they are laser powered. So we have let go of actual soldering for mass production. That era has passed. Of course, if it's a small run thing, it would be cheaper to just like do that. And even those scenario, people have their own small scale pick and place machine, have their own pick and once you have the pick and place machine, you just send it in an oven. And you also have vapor soldering, which allows you to have very precise temperature control. So if you need something like that is sensitive, that does not require that even a remote chance of overheating it, people use that. So mass production has reached the point where soldering is gone. So we no longer have to worry about these things or cold joints or less fitting. It's like, if done correctly, proper testing is done, you're gonna have flawless result without any issue. But you must take care of your tips. Tips requires caring, because if you like have copper tips, if you do not take care of them reliably, regularly, they're not gonna last. And even if you have iron tips, you may be like, hey, shiny iron, everything is fine, it has coating, it has chrome coating, it has nickel coating here, everything is fine. Not necessarily. After using it, because here's the deal, what are you putting this tip through? You're putting this tip through a lot of heat, and you're putting it in an oxygen environment, aka our atmosphere. So things do react over time. And not to mention, you are also introducing flux to it. That puppy is designed to eat through layers of oxidation. So over time, it eats through it, it goes down, goes even deeper, and voila, your coating is no more. Without coating, these things do not last. You do not want oxidized tip. You always want tint tips. So the easiest way, whenever you are done with your work, make sure you clean the tip, put fresh solder in there, then turn off. You do not let it be naked. If it's naked, it's not gonna last. No matter what coating you have. It's like, even JVC will tell you, they have a whole guide. How do you keep your tips healthy? If you're not, they are happy. They're like, hey, buy new tips. Station, hey, you don't have to buy the station, just keep buying tips. So it's better to learn how to take care of the tips. And if you are that kind of individual who are like, I'm gonna learn how to basically electroplate at home, which is not that difficult, yeah, then you can have a forever tip. So be very mindful of those sort of things. And nowadays, generally, it's not recommended, especially if you're working with lead-free solder, to use a wet sponge. Be mindful, most people do not put this deionized water there, and most of the time, they do not even have proper high temperature foam there. So use these puppies, much better at higher temperature, and does not cause boom boom effect on the basically tips. Tips touching water is causing cavitation there. So it's literally the coating away. You do not want that, especially at high temperature ones or lead-free ones. Use this, much better, much cheaper. So you must take care of your tips. Now, what are you paying for? Because many stations, even the Chinese ones, compared to price of these one, they're exponentially expensive. They're like expensive, painfully expensive. Why? Well, what you are paying for is speed. If your tips to basically tip to energy distance, basically how much energy needs to be dumped, it can be done efficiently. You can work quickly. And here's the ease of use. How easy it is to set up the system where it's like, hey, just this solder, press this button. It's like, I got this. I'm going to set the configuration to this. You do not overfry it or do not overheat it. Or you're like, hey, I'm working with something very small. I want even less temperature delta, so I do not flood the drying micro devices, basically. Ease of use, that's what you are paying for. And on top of that, the biggest desirable thing is what we call tip distance, meaning if you have a very cheap soldering iron, this is the best you can expect. Okay, now if you have a bit more money, not too much more, not exponentially more, see the tip difference. JVC, it's almost like this. So, and you're like, is that 1 inch worth of the price? Yeah. Ask a surgeon why the scalpel is like, almost like this. There is a reason for it. It's like doing like this, not good. Doing like this, oh, okay. Doing like this, better. Doing exactly like this, really good. So that's the key aspect here. Small tip to finger distance, and be mindful to do that. You have to use expensive materials, because again, the heat source is here. If your finger is here, the insulation around it has to be A, high temperature rated, B, has to be very low flux through. So like it has to last very long. It's expensive. Like you have to use very high grade silicones and other stuff. Can be done, it's just expensive. So it's an art form. Do not get too hung up around it. Take care of your tips and understand what you're paying for, and you're gonna have a jolly old good time. These are generally used for brazing, copper tubes for air conditions and things of that nature. Please tell me where I can find videos of this. These are amazing. I want to see it in action. So this was my presentation on soldering. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.